In this movie, we are going to review basic theorems and properties of Laplace transform. You would remember from your differential equations course that using Laplace transforms, we can convert differential equations to algebraic equations and therefore solve them in an easy way. Let us call the Laplace transform of a function f of t as capital F of s. The function f of t and its Laplace transform f of s are also called a Laplace transform pair. The Laplace transform of f of t is given by this integral. Note that the integral is over the variable t, so that the result is a function of s. We will show this operation on the function f of t by a large script L referring to Laplace transformation. The variable t is not necessarily but usually the time variable, whereas s is a frequency domain variable. If you have a Laplace transform capital F of s, you can obtain the corresponding time function by an inverse Laplace transformation. Note that the integral defining the inverse transformation is a line integral in the complex plane parallel to the imaginary axis. The integral may look complicated, but we will hardly use this integral for finding an inverse transform. We shall adopt much easier methods. Also, since f of t contributes to the Laplace integral with its values t greater than 0, we shall assume that f of t is equal to 0 for t less than 0 without any loss of generality. Let's obtain the Laplace transforms of some frequently used functions. This is an exponential function. To obtain its Laplace transform, we use the Laplace integral. Note that the integral will converge only if the exponent minus s plus a times t is negative. Therefore, the resulting transform 1 over s plus a is valid for all s greater than minus a. The second example is a step function of amplitude capital A. Here, the symbol shown as a bold digit of 1 refers to the unit step function, that is, the step function of amplitude 1. Using the Laplace integral and proceeding as in the previous example, we obtain the Laplace transform as a over s. Note that this time the Laplace integral converges for positive values of s. Nevertheless, by analytic continuation, we can consider both Laplace transforms as valid over the entire complex plane. Let us now consider a sinusoidal function. The Laplace transform in this case can be obtained more easily if we express the sinusoidal function in terms of complex exponentials. So we have two exponentials to integrate. We can write the integral functions and evaluate them between 0 and infinity. And simplifying the resulting term, we can obtain the Laplace transform of sine omega t as omega divided by s squared plus omega squared. We shall now go over some properties of Laplace transform, which will be useful for us in the forthcoming lectures. Maybe the most important property of Laplace transform is its uniqueness. In other words, if a function f of t has a Laplace transform as capital F of s, then it is the only inverse transform of capital F of s. The uniqueness property enables us to convert functions between the time domain and frequency domain without any ambiguities. The Laplace transformation is also a linear operation. That is, if you multiply any time function f of t by a scalar, say small a, then the corresponding Laplace transform is also multiplied by the same scalar. Also, the Laplace transform of sum of two functions can be obtained as sum of the Laplace transforms of individual functions. Obviously, Laplace transform inherits its linearity property from the linearity property of integrals. Another important property of Laplace transform is the translation property, which can be stated as follows. If you mask a function for negative values of t and translate it on the time axis by, say, a units, then the Laplace transform of the translated function will be equal to the Laplace transform of the original function multiplied by e to the power minus as. In other words, we can say that translation in time domain corresponds to multiplication by an exponential function in frequency domain. Here is how you can prove this property. First of all, these figures show you an example of how a function masked for negative values of t and its translation may look like. Now, we can start the proof by directly writing the Laplace integral for the translated function. Let us now make a change of variable and write t minus a as tau. This also changes the lower integration limit from 0 to minus a. Note that the integrand has a unit step function as a factor. Therefore, the lower integration limit can be reset back to 0 since the integrand is 0 for negative values of tau. And finally, taking the term e to the power minus sa out of the integration sign, we see that the remaining integral is the Laplace transform of f of t. So this proves that the Laplace transform of the translated function is equal to the Laplace transform of the original function multiplied by e to the power minus sa. Let us use the translation property to obtain the Laplace transform of a pulse function. The pulse which we are going to consider here is of duration t sub 0 and of amplitude capital A by t sub 0. Note that such a pulse function can be written as the difference of two step functions, namely one having its step at the origin and the other one with a step at t sub 0 seconds. So by using the Laplace transform of a step function and the linearity of the Laplace transformation, we can obtain the transform of such a pulse as a over t0s multiplied by 1 minus e to the minus s t0. An important special case of the pulse function is when you take its limit as t sub 0 goes to 0. This gives us the so-called impulse function. Note that the area under our pulse is capital A, which is also valid in this limiting case. So the impulse function is 0 for almost all values of t, yet its integral from minus infinity to plus infinity evaluates to something non-zero. The Laplace transform of an impulse function can be obtained from that of the pulse function by applying the same limit. By using L'Hopital's rule, this limit can be shown to be equal to capital A. In the case where A is equal to 1, we have the unit impulse function, which is also called as Dirac delta function. So the impulse function integrates between minus infinity to plus infinity to 1, and it is 0 almost everywhere. Also note that it can be expressed as the derivative of the unit step function, and its Laplace transform is equal to 1. Another property of the Laplace transformation is the frequency translation property. Let's use the Laplace integral in order to compute the Laplace transform of f of t multiplied by an exponential function. collecting the exponential terms together, we can easily recognize that this is nothing but the Laplace transform of f of t, except that s is replaced by s plus a. In other words, multiplying a function by an exponential term in the time domain results in the translation of its Laplace transform in the frequency domain. For example, since we know that the Laplace transform of sine omega t is omega by s squared plus omega squared, we can write the Laplace transform of the same sinusoidal function multiplied by an exponential term as omega divided by s plus a squared plus omega squared. We also have an interesting time scaling property of Laplace transform. Assume that we expand our time axis by a factor of a. This will be equivalent to replacing our time variable t by t over a. Let's try to obtain the Laplace transform of this time-scaled function. Again, we start by writing the Laplace integral for this function. We do a change of variables so as to denote t over a as tau. We shall also use the variable r wherever we have a times s. Now, we see that the resulting integral is the Laplace transform of f of t, save that it is multiplied by the scalar a and the variable s is replaced by r. By substituting r with a times s, we can obtain the Laplace transform of the time-scaled function. Note that a scaling in time domain corresponds to a scaling in frequency domain in the reverse sense. That means an expansion of the time axis means a contraction in the frequency axis. For example, remember that we obtained the Laplace transform of e to the minus t as 1 over s plus 1. Since e to the minus 0.2t can be considered as f of t scaled by a factor of 5, in other words, f of t over 5, its Laplace transform can be obtained easily by this property as 5 over 5s plus 1. At this point, we have to note an important fact related to the lower limit of the Laplace transform. Let's assume that the function f of t has an impulse at t equals 0. In this case, the integrals starting at 0 plus and 0 minus involving this function will not be equal. By 0 plus, we mean the instant infinitesimally close to 0 on the right, and by 0 minus, we mean the instant which is also infinitesimally close to 0 on the left-hand side of 0. If the lower limit of the integral is 0 plus, an impulse at the origin will not contribute to the integral, whereas it will if the lower limit is 0 minus. We distinguish between these two different versions of the Laplace integral as L plus and L minus. In fact, L minus will be sum of the integral L plus and an integral from 0 minus to 0 plus. Therefore, it is important to denote the lower limit of the Laplace integral whenever f of t involves an impulsive behavior at t equals 0. Of course, if f of t is finite and smooth around 0, these two versions of the Laplace integral will be equal. Another interesting property of Laplace transform can be stated as follows. The Laplace transform of the derivative of a function is the Laplace transform of the original function multiplied by s minus the value of the function at t equals 0. It is interesting to note here that the value of the function in time domain explicitly appears in the Laplace transform. To prove this property, we are going to start again with the Laplace integral of f of t. At this point, remember the integration by parts theorem. if you can express the integrand in an integral as u times v prime, where prime denotes differentiation, you can obtain this integral as u times v minus the integral of u prime v. To apply an integration by parts, we first recognize f of t as u and e to the minus st as v prime. So v is going to be e to the minus st divided by minus s. And u prime is simply the derivative of f of t. Evaluating the first term and taking minus s out of the integral in the second term, we see that the remaining integral is a Laplace integral. In fact, it is the Laplace integral of the derivative of f of t. Now, multiplying both sides of the equation with s, we can solve for the Laplace transform of the derivative of f of t as s times capital F of s minus f of 0. Of course, similar formulas are valid also for L plus and L minus transforms, which we have defined just a while ago. You can apply the differentiation property of the Laplace transform to obtain also the Laplace transform of the second derivative of the function. That is, you can consider the second derivative of a function as the derivative of its derivative, apply the differentiation property for the outer differentiation, and then use it again to express the Laplace transform of the derivative of f of t in terms of capital F of s. Note that capital F of s is now multiplied by s square. Proceeding in this way to higher derivatives, we realize that the Laplace transform of the nth derivative of f of t will involve capital F of s multiplied by s to the power n, and also initial conditions of the lesser derivatives of the function. As an example of application of the differentiation property, let us consider the Laplace transform of sine omega t and obtain the Laplace transform of cosine of omega t. In fact, cosine omega t is the derivative of sine omega t divided by omega. Now, using the Laplace transform of sine omega t in the differentiation theorem and noting that sine of 0 is 0, we can show that the Laplace transform of cosine omega t is s divided by s square plus omega square. Now, we are going to introduce two important theorems that link the limits of Laplace transform pairs in time and frequency domains. The first one is the final value theorem. It states that the limit of a function as t goes to infinity is equal to the limit as s goes to 0 of its Laplace transform multiplied by s. Here we assume that the derivative of the function is Laplace transformable and the limits on both sides exist. So the theorem itself does not guarantee the existence of the limits, but is valid if the limits exist. To prove the theorem, we recall the differentiation property of Laplace transform. Let us now express the derivative of the Laplace transform of f of t with a Laplace integral and take the limits of both sides as s goes to 0. Of course, e to the minus st term in the integral will disappear since it evaluates to 1 for s equals 0. And now, remembering the fundamental theorem of calculus, the integral of the derivative of f of t is equal to f of t, and finally cancelling f of 0 on both sides, we obtain the final value theorem. The other theorem is the initial value theorem, which states the initial value of a function is equal to the limit as s goes to infinity of its Laplace transform multiplied by s. Here, f of 0 plus indicates the limit on the right as t goes to 0. Again, we assume that the derivative of the function is Laplace transformable and the limit on the right-hand side of the equation exists. To prove this theorem, once more we start with the differentiation property of the Laplace transform. This time we use the Laplace transform and replace it with the Laplace integral. We take the limits of both sides as s goes to infinity. Note that the integration interval is from 0 plus to infinity. So in this interval, t is never equal but always greater than 0. Therefore, as s goes to infinity, e to the minus st will evaluate to 0. Reducing the left-hand side of the equation to 0 and rearranging the terms, we obtain the initial value theorem. Having reviewed the Laplace transform of the derivative of functions, let us now consider the Laplace transform of the integral of a function, which is given by the so-called real integration theorem. This theorem states that the Laplace transform of an indefinite integral of a function f of t is equal to its Laplace transform divided by s, plus the initial value of this indefinite integral divided by s. To prove this, apply the Laplace integration formula to the integral of f of t. At this point, we are going to proceed by an integration by parts. Considering the integral of f of t as u and e to the minus st as v prime, we can write the integral in two terms. In the first term, e to the minus st evaluates to 0 as t goes to infinity. Therefore, what remains from the first term is its value at t equals 0. In the second term, we take minus s out of the integration sign. So this integral is now capital F of s. And that gives us the Laplace transform of the integral of f of t. Applying similar arguments, you can show that the Laplace transform of the definite integral of f of t between 0 and t is simply equal to capital F of s divided by s. And similar formulae hold for L plus and L minus transforms for integrals with lower limits as 0 plus and 0 minus respectively. To sum up, you can simply say that integration in time domain means division by s in the frequency domain. A dual of the theorem of differentiation in time is the complex differentiation theorem, which relates the derivative of a frequency domain function f of s to its time domain counterpart. It is interesting to note that the differentiation in frequency domain corresponds to multiplication by t in time domain. Writing the Laplace transform of t times f of t, we see that in the integrand we have t times e to the minus st, which is nothing but the negative derivative of e to the minus st with respect to s. Since t and s are independent variables, you can interchange the differentiation and integration operations. And the remaining integral simply becomes the Laplace transform of f of t, which proves the theorem. To obtain the Laplace transform of t squared times f of t, you can apply the complex differentiation property twice. In fact, you can also generalize this idea to the Laplace transform of t to the n times f of t. So we see that each multiplication by t in time domain corresponds to a differentiation with respect to s in the frequency domain, and also a multiplication by minus 1. The last theorem we are going to review is the famous convolution theorem. Let us consider two Laplace transform pairs, that is, f1 of t has the Laplace transform capital F1 of s, and f2 of t has the Laplace transform capital F2 of s. In a while, we are going to prove that the integral from 0 to t of f1 of t minus tau times f2 of tau has the Laplace transform given as capital F1 times capital F2. This integral is known as the convolution integral and is denoted by a star. In other words, convolution in time domain corresponds to multiplication in frequency domain. Let us first show that convolution is a commutative operation. That means F1 convolves F2 is equal to F2 convolves F1. To show this, we write the convolution integral of F1 star F2 and do a change of variables so that lambda equals t minus tau. Note that if tau equals 0, lambda equals t, and if tau equals t, lambda equals 0. So now the integral is from t to 0. Also d tau is minus d lambda. Therefore, we have a minus sign in front of the integral. You can absorb this minus sign into the integral by exchanging the integration limits. In doing so, what we obtain is nothing different but f2 star f1, which proves that convolution is a commutative operation. Let us now prove the convolution theorem. We start by considering the Laplace transform of f1 convolves f2. Since the unit step function of t minus tau will be 0 for tau greater than t, we can introduce this function into the integrand and extend the upper integration limit from t to infinity. So such a unit step function will mask the integrand for values of tau between t and infinity. Next, we write the Laplace integral for the function in curly brackets. Now we can interchange the integrals of tau and t, and since f2 of tau does not involve the variable t, we can take it out of the inner integration. Then we can do a change of variables so that lambda equals t minus tau. Here we can remove the unit step function of lambda since the integration limits for lambda are 0 and infinity. Now factorizing the exponential terms into two exponentials and separating the terms to be integrated over lambda and over tau, we notice that these integral factors are in fact capital F1 of s and capital F2 of s. So this proves that the Laplace transform of the convolution of two time functions is equal to the product of their Laplace transforms. Up to now, we have considered finding the Laplace transforms of different time functions. What about the inverse problem? That is, finding a time function corresponding to a given frequency domain function. In this case, one has to apply inverse Laplace transformation. Remember the formula we introduced for inverse transformation, which is a line integral over a path parallel to the imaginary axis in the complex plane. In many cases, this integration may not be easy to evaluate, and a more convenient way to obtain inverse Laplace transforms would be to use tables of transforms. If you know the Laplace transforms of certain basic time functions, you can express your frequency domain function to be inverse transformed in terms of their transforms. In fact, in studying the linear systems, we shall encounter Laplace transforms in the form of real rational functions. That is, they will be in a form like p of s over a of s, where a and b are polynomials in the variable s with real coefficients. We will make two assumptions for such real rational functions. The first one is that the degree of the numerator polynomial is less than the degree of the denominator polynomial. We call such a rational function as a strictly proper rational function. In some cases, we will relax this condition so as to assume that the degree of the numerator polynomial is not greater than the degree of the denominator polynomial. In this case, the rational function will be a proper rational function. Our second assumption is that the denominator polynomial is monic. In other words, the coefficient of the highest power of s is 1. Note that this assumption does not introduce any loss of generality, because if a is not monic, you can divide the numerator and the denominator polynomials to the coefficient of the highest power to make the denominator polynomial monic. The most frequently used method in inverse transforming real rational functions is the partial fraction expansion method. To apply the partial fraction expansion method, let us first factorize the numerator and denominator polynomials into first-order terms. And also remember that we have assumed that f of s is a strictly proper rational function. The polynomials a and b have real coefficients. Nevertheless, the constants z and p can be real or complex. A rational function in this form can be expressed as a sum of fractions with denominators of degree 1. The negatives of the coefficients p1 to pn are called the poles of this rational function. And a sub k is the residue of this function at the pole s equals minus pk. In order to find out how the residues can be obtained, let us multiply the function f of s with s plus pk and evaluate the result at s equals minus pk. Now, if we consider the expansion above, we see that all terms will be equal to 0 except the kth one, where we have a cancellation of s plus pk terms in the numerator and in the denominator. So what remains from the function is only a sub k. That also should explain why a sub k is called the residue at this pole. Also note that the expansion we wrote above is a linear combination of the Laplace transforms of exponential functions. So applying the linearity property of the Laplace transform, we can write the inverse transform of capital F of s as f of t, which is equal to a linear combination of exponential functions. The exponent of each term is a pole multiplied by t, and the coefficient of each term is the residue of the function capital F of s at that pole. Let us now find the inverse Laplace transform of f of s given as s plus 3 divided by s plus 1 times s plus 2, which can be written as a sum of two fractions with denominators s plus 1 and s plus 2. To find a1, we multiply f of s by s plus 1 and see that the s plus 1 terms are cancelled, and evaluate the rest at s equals minus 1, which results in a1 equals 2. Proceed similarly for a2, that is, multiply f of s by s plus 2 and evaluate at s equals minus 2. That gives us a2 is equal to minus 1. Having written f of s as in this form, we see that the first term is the Laplace transform of 2 times e to the minus t, and the second term is minus the Laplace transform of e to the minus 2t. So by applying the linearity property of Laplace transform, we can write the inverse transform as the combination of these two time functions. Here is another example. Note that in this case we have a real rational function where the numerator degree is larger than the denominator degree. Therefore, we first apply a polynomial division to separate the polynomial and the strictly proper parts of this rational function. Here, the inverse transform of the third term is already known to us from the previous example. On the other hand, to find the inverse transform of s plus 2, remember that the Laplace transform of the unit impulse equals 1. Therefore, the inverse transform of 2 should be 2 times the unit impulse function. Also note that differentiation in time domain corresponds to a multiplication by s in frequency domain. By considering s as s times 1, we can conclude that the inverse transform of s is the derivative of the inverse transform of 1, that is, the derivative of the unit impulse function. Finally, since the inverse transform f of t has an impulsive behavior at t equals 0, its domain should start from 0 minus. Let us now consider another example with capital F of s having again a second order denominator. If you factorize the denominator into first order factors, you will get complex coefficients. Of course, you can still proceed with a partial fraction expansion here, but we can take a shorter cut if we remember the Laplace transforms of sine and cosine functions multiplied with exponentials. In order to figure out a term like s plus a squared in the denominator, let me separate the term s squared plus 2s plus 1, which is a complete square, in fact the square of s plus 1. Now, f of s can be written as the sum of two terms with denominators s plus 1 squared plus 4. These two terms match the formulas of Laplace transforms of sine and cosine functions multiplied with exponentials, where a equals 1 and omega equals 2. So, using the linearity and the uniqueness properties of the Laplace transform, the final result is obtained as f of t equals 5e to the minus t sine of 2t plus 2e to the minus t cosine of 2t. In all our examples up to now, we had functions to be inverse transformed having distinct poles. But what if capital F of s has multiple poles? Let us show how this case can be dealt with in an example. Here we have a rational function with the denominator s plus 1 cubed. In this case, we are going to apply a partial fraction expansion with denominators s plus 1, s plus 1 squared, and s plus 1 cubed. If we multiply capital F of s by s plus 1 cubed, we will get a full cancellation of s plus 1 term only in the third fraction. Therefore, evaluating the result at s equals minus 1, we can obtain the coefficient b sub 3. Then you can evaluate the derivative of s plus 1 cubed multiplied by capital F of s at s equals minus 1 to get b2, and proceed with the second derivative of the same function to obtain the coefficient b sub 1. Since multiplying capital F of s with s plus 1 cubed gives you the numerator polynomial, you can simply evaluate s squared plus 2s plus 3 and its derivatives at s equals minus 1 to find the coefficients of the partial fraction expansion for capital F of s. This example suggests such a formula for calculating the residues. Small case m is the multiplicity of the pole, so you can find m residues for such a pole. Also, for m equals to 1, that is, if we have a distinct pole, we obtain the formula which we have derived for calculating the residues corresponding to distinct poles. To conclude this chapter, we are going to consider an example where we can apply Laplace transforms to solve a linear differential equation. Consider the equation x double dot plus 3x dot plus 2x equals 0 with the initial conditions x of 0 is a and x dot of 0 is equal to b. Here we are using dot to denote differentiation. Let us show the Laplace transform of x of t with capital X of s. Remembering the differentiation property of the Laplace transform, we can easily write the transform of the first and second derivatives of x of t in terms of capital X of S. Now apply Laplace transformation to both sides of the differential equation. Doing so, we obtain an algebraic equation corresponding to this differential equation. Therefore, the rest proceeds easily. You can solve for capital X of S and apply a partial fraction expansion for it. And finally, you can apply an inverse transformation to obtain the solution of your differential equation in time domain. In this chapter, we have reviewed basic theorems and properties of Laplace transform and inverse transformation by using partial fraction expansion. Having finished this chapter, you can go over other examples in your textbook to check that you can use Laplace integral to obtain Laplace transforms. You can compute Laplace transforms of piecewise smooth functions by expressing them as combinations of basic functions. You can make use of properties of Laplace transform in finding transforms of time functions. You have an understanding of physical and mathematical meaning of the impulse function. You can use tables of Laplace transforms to find inverse Laplace transforms of frequency domain functions. And you can solve constant coefficient linear differential equations using Laplace transformation method.